So hello and welcome back. Today we will have our lecture on power factor correction when we have a load that has a lagging power factor and we need to put a capacitor in parallel with the load in order to improve the power factor. Remember, the closer the power factor is to 1 or the power factor angle is to 0, the more efficient the delivery will be of the power to the load from the power plant or the energy source. Stay tuned. So students should be reading chapter 9 of their textbook as well as Dr. Gregg's notes, pages 82 to 87, to learn more about this topic. Remember, you sometimes may have to watch the videos more than once, read the lecture or the textbook more than once to get it. Upon completion of this lecture, students should be able to use power factor correction to improve the power factor for a load and use the short circuit and open circuit test to find transformer parameters. Please note that this focus is only on power factor correction, as previous videos have already been created that show how to implement the short circuit and open circuit method to find transformer parameters. So power factor correction is essentially a way for a system to be more economic by reducing the power loss in the feeder line when delivering real power to a load from a source. Power factor correction is the process of improving the power factor of a load by reducing the overall reactive power. The process of increasing the power factor without alternating the voltage or current to the original load is called power factor correction. Most domestic loads such as washing machines, air conditioners, refrigerators, etc. are inductive and have a low power factor. As we've already stated, the higher the power factor, the more efficiently the power company can deliver the average or real power to the load. So power companies will charge more for larger currents because the result in increased average power loss in the line or the feed. Therefore, it is beneficial for a power company to have consumers to increase the power factor, getting it as close as possible to unity to be the most efficient for delivering power. When you have a lagging load, the power factor is improved by installing a capacitor in parallel with the load. The following figures show what this looks like. You have an inductive load modeled as a resistor and an inductor, and it has a given power factor. We don't want the average power to change, so by putting the capacitor in parallel with that load, it will only affect the reactive power, which we want to reduce. And by reducing it, we take the initial power factor angle theta 1 and change it to theta 2. These following two figures show what happens when you do that. So if you look at it in terms of the lagging current, the original current is theta 1, and the new current delivered to this parallel load would now be I, where it goes from theta 1 to theta 2. Notice that the real part would still be the same, but the power factor angle would change. You can also represent this as a power triangle with power factor correction, where you would have your original reactive power Q1, the new required or desired one Q2, which takes it from theta 1 to theta 2. So then you subtract off QC in order to go from Q1 to Q2. So improving the power factor means that you want it to look less inductive to the current at the source. Less inductive and more resistive means essentially you're going to subtract off some of the reactive power so that the average power appears to be the larger of the two values if possible. Getting the power factor as close as possible to 1, reducing the magnitude of the current drawn by the source, which then also reduces the power loss in the line. So the formulas we use to do this are that if the apparent power is S1, then P1 is S1 cosine theta 1, and Q1 is S1 sine theta 1, or P tangent theta 1. So you're going to model the original system by finding the values for P, Q1, and S1. Then we need to find our new reactive power Q2 by using the same P, but now the new theta 2. So Q2 would be P tangent theta 2. And then I find the value of the reactive power for the capacitor by using QC equals Q1 minus Q2, or P times tangent theta 1 minus tangent theta 2. Once you have QC, you can now use the formula VRMS squared over XC, which is the RMS voltage at the source divided by the reactance, and you can then solve that for omega C VRMS squared, or C is equal to QC over omega VRMS squared. Notice in this entire process, P, the real power or the average power to the load, does not change, only the reactive power changes. And because of this, the average power to the capacitance is going to be 0. So by adding that capacitor, it does not change the real power. It would only affect the reactive power. Now let's take a look at some examples.